Hello, Physics 2 people. So in this video, I want to talk about sort of the simplest possible AC generator design. I mean, this wouldn't be the most practical design, but it catches the idea of it. And the output will be AC current, so it's going to be I guess we'll talk about voltage. So we're going to get an EMF, which is time dependent, sinusoidally time dependent. So the basic idea is as follows. Imagine you have two, we'll let them be permanent magnets, north and south. And then we're going to have a loop of wire, which we're going to rotate with some angular velocity, omega, right? And as always, there is a surface which spans across that. So we're going to imagine I have a surface here. Put that in blue. And I'm going to imagine that I have a normal vector to the surface. Okay, that'll be my normal unit vector. Okay. We'll go ahead and take the magnetic field to live, let's say it's in the z direction, some constant b, we'll take it to be a constant uniform magnetic field in the z direction. And so we have to think about this, and as the normal vector rotates around with an angle, or sorry, the angle it makes with respect to the z-axis is going to change. So I'm going to assume, I'm not sure my picture quite matches up with this, but I'm going to go ahead and assume that the normal vector as it rotates is just going to be something simple like sine of theta x hat plus cosine theta z hat. So basically, every so often the normal direction the magnetic field will point in the same direction, when theta is 0 or pi, and so on. And then at when it's 90 degrees, it'll point perpendicular in the x direction. All right. Immediately, and I should also say this, if the angular velocity is omega, we have that theta equals omega t. So that's kind of where t is time. So if we want to do this, well, you can see as the wire rotates, the magnetic field lines that pierce the surface are going to be time dependent. So the flux is going to be time dependent, and we're going to generate an EMF around the base of that loop. So let's write out the magnetic flux. That's simply going to be, so that's the integral of B dot dA. That's going to simply be B naught times the area of the loop. And then the dot product between them is going to pick out the cosine of theta. And if I think of theta in terms of time, I can write that as B naught A cosine of omega t. All right, so that's the flux. The magnetic flux is a function of time, and it is a cosine dependence. Fine. Now the EMF around that loop is simply going to be minus the time derivative on the magnetic flux, and so that's going to be minus B times A times the time derivative on cosine of omega t, which is simply B times A times omega times the sine of omega t. Awesome. So what we get, so if you were to, so we have this square that's rotating, and if you were to measure the difference in potential or measure the voltage with a voltmeter between points A and B, you would get a curve which looks like that. So this would be the EMF around this loop. It would go up and down sinusoidally. The period would be 2 pi over omega, as usual. And you would also have the max EMF would just be this prefactor, be omega times B times the area of the loop. So that's kind of interesting. So we find that the peak, so let me rewrite that. The peak EMF sorry. The maximum EMF, which is omega times B times A. So how do you think of it? Well, so it should depend upon the time rate of change at which you catch field lines. So it grows with omega. That means you just cycle between positive flux and negative flux faster and faster and faster. So that makes sense. It grows with the magnetic field, right? The overall amplitude or the overall magnitude of the magnetic field just tells you the overall number of magnetic field lines. And so as you swing from positive to negative, you get a bigger change. And then also it grows with the area because you simply catch more field lines with bigger area. So that's kind of how to think of it. When you have, you have this EMF which goes up and down, up and down, up and down. So the average EMF is 0, right? Half the time EMF is positive, half the time it's negative. The average value is 0. But, that's not really the quantity we care about. When we compute power and things, we often get EMF squared. So we don't want to think about, we want a quantity which doesn't have cancellations. So another, I guess, if you want the typical size, the typical magnitude of the EMF, well, that's not 0. I mean, the EMF is only 0 at a few places. So that's not really what we care about. If we want the typical size of this thing, well, on average, it typically isn't 0. It's typically, I don't know, something like this, as I shake my stylus back and forth. So what we want to do is come up with a way of estimating that. And that's going to be the RMS value, the root mean squared of the EMF. So remember, RMS means square it. So it's the square root of the average of the square. Okay, so you take the square root of the average of the square. So in this case, we want to find the average of the EMF squared and then take the square root of that. That is going to be the RMS value. Now, there are two ways to do this. The long-winded way to say it is, ultimately we're going to need the average value of sine of omega t, sorry, sine squared of omega t, and the average value, you'd use the mean value theorem of integral calculus. So you'd say it's 1 over the period times the integral of sine of omega t squared dt from 0 to 1 period. Or, you can do that. Or you can look at the graph. So if you think about sine squared, it oscillates between 0 and 1, but it's never negative, and the average value is a half. So in fact, the answer for this average value is a half. Just from the graph is the easiest way to do it. Or you can do the integral. You integrate by parts twice, rearrange it. It's one of those where you integrate by parts twice, and you start with sine squared, and you end up with sine squared on the right-hand side, and you rearrange it and solve for the integral you want. Okay, so all that being said, what we find is that the average value for the EMF squared is going to be, well, that's going to simply be omega times b times the area squared times the average value of sine squared of omega t, which just gives you a half. So this is just omega squared b squared area squared over 2. And take the square root of that to find E RMS equals omega BA over square root of 2, which is conveniently written as the maximum value over the square root of 2. When things oscillate sinusoidally, it's very common, if not always actually, you get the RMS value is going to be 1 over the square root of 2 times the peak value. So that's just a useful formula. It'll come up a couple times in sapling. All right, so let's kind of recap. By spinning a loop in a magnetic field, you generate a time-dependent flux, and then by working out the details of that, you see that you get a time-dependent EMF, and it's sinusoidal, so that's called an alternating or an AC power supply or AC generator, because it's going to give rise to alternating currents, sometimes positive current, sometimes negative current. You can think of this as being due to 3 effects. One is a speed effect, one is a magnetic field strength effect, and one is just an overall area effect. And then here at the end, I also went through how you would come up with averaged quantities, which are what are typically quoted when you talk about a generator that generates so many volts, or even out of the wall. We talk about the voltage coming out of the wall. Well, it's an AC voltage, so it goes up and down, up and down. The average value of the voltage is actually 0, but when we talk about the 110 or 220 volts coming out of the wall, then what we're actually quoting here is an RMS value. Actually, I have to think about that here. Is that RMS or is it peak? Let me think about that. I think that's I think when we say, generators at 220 volt, that's the RMS value. We're not quoting the peak value. I believe that's right. Anyway, if this is wrong, give me feedback in the comments below. Okay, so that's all for this one. In the next video, I'm going to talk about something called a homopolar generator. So it makes a DC power supply. And it's a little trickier to wrap your mind around. So, all right, catch you next time.